In our last video, we covered trig substitution. In our second to last video, we covered basic trig integrals. And as foretold in my trig substitution video, today we are moving on to level 3, advanced trig integrals. Now, while the word advanced might sound very scary, in reality, this is just a very logical extension of the stuff we've already learned. In reality, it won't be this bad at all, and I'm sure that you will enjoy it a lot. So, without further ado, let's get to solving some problems. The first problem that we are going to cover is this: the integral of sine cubed x dx. So, let's go on to solving this problem. Now, if you do know this problem, and if you do understand this concept and you're using this channel to practice, feel free to pause the video and solve the problem on your own before coming back to check your answer at the end. So, now, let's go on to actually solving this. So, what do we know? Well, we know the integral of sine of x dx. We know the integral of cosine of x dx. And we know the rest of the basic trig integrals. But what about sine cubed x? Why is there a cubed power? That makes no sense. Like, what are we supposed to do? Well, let's look at it like this. We know the integral of sine of x, so let's factor out sine of x first and see if that gets us anywhere. So we have sine of x multiplied by sine of x squared, or sine squared x dx. So we have the integral we know, but there's also something else that we don't know. But now it's time to recall another technique. Yeah, I know there's a bunch of techniques, but this is what makes calculus so interesting, that you can weave together all of these different techniques, everything else, and merge them just to solve one problem. And it's a very, very fun problem solving exercise and helps boost a lot of skills. So, believe it or not, we're going to convert it into cosine of x. But how do we do that? Well, by the Pythagorean identity, sine squared x plus cosine squared x is equal to 1. So sine squared x is equal to 1 minus cosine squared x. So this is equal to the integral of sine of x times 1 minus cosine squared of x dx. So that's good. And now, just by basic algebra, let's distribute. Let's bring this problem over here. So sine of x dx integral minus the integral of sine of x cosine squared of x dx. So now we know that we can evaluate our first integral as negative cosine of x, but we still have our integral of sine of x cosine squared of x dx. Now, instead of trying to simplify this more, well, really we are going to simplify it, but instead of trying to use more trig identities, why not we find a way to remove this sine of x from the equation? Because if we can just get an integral talking about cosine of x, we might be able to solve it easier. Or if we could remove the cosine of x, that could also work. But in this problem, we're going to remove, quote unquote, the sine of x by plugging in cosine of x is equal to u. And that's another technique, the other technique I was talking about, which is our good old u substitution. So, cosine of x is equal to u. Then what we have is du is equal to negative sine of x dx. So sine of x dx, which is in our equation, is equal to negative du. So now we get negative cosine of x plus, because a negative times a negative is a positive, then we have the integral of u squared du, and integrating this gives us u cubed by 3 minus cosine x plus c, which then gives us cosine cubed of x over 3 minus cosine of x plus c. And there you have it. There is the integral of the actual equation, our integral of the equation, which is cosine cubed of x over 3 minus cosine of x plus c. Now you might be like, huh? That's so many steps. I don't completely understand it. For that, of course, you can always rewatch this until you get it. But another great and helpful strategy would be to make sure that you try this problem on your own and try and discover these steps on your own, and maybe look for alternatives. Maybe you found a different method that ends up being the same. It's always good to try stuff on your own so you can discover as much as you can about everything else. But enough with this first problem. Let's move on to the next one. This problem states the integral of cosine squared of x dx. Alright, so what do we have here? Well, we know, as we know earlier, we know our sine, cosine integrals, but this time we have cosine squared, not cosine cubed, so we can't do our trick of isolating one cosine and then having cosine 1 minus something and then have all of that handy dandy. But now we have to use something different. But luckily for us, one tool was basically made for this problem. It looks like when they made that identity for trig, it was created pretty much to solve this problem with very few extra steps. And that identity is, drumroll, the cosine squared identity, or the double angle identity for cosine. This double angle identity states that cosine of 2x is equal to 2 cosine squared of x minus 1. Now, if you're confused about this identity and where it came from, be sure to check out my video on this in my trig series. All the series are on my channel, and it should be pretty easy to find that identity in that series. So, without further ado, let's actually go on to solving this. But before we solve it, we know what cosine of 2x is. But how will we figure out what this is? Cosine squared of x. This makes no sense. We don't have it in terms of cosine squared of x. So what are we going to do? We're going to make it in terms of cosine squared of x. So we have cosine 2x plus 1 is equal to cosine squared of x. 2 cosine squared of x, and 1 by 2 cosine of 2x plus 1 is equal to cosine squared of x. So we can rewrite this integral as 1 by 2 of cosine of 2x plus 1 dx. Now, separating this out gives us 1 by 2 times the integral of dx, which is just x, so 1 by 2x, plus the integral of cosine 2x dx. Now, if we just do u substitution with u is equal to 2x, and I forgot to mention this in my last problem, But if you don't know what U substitution is, check out my video in the calculus series on that. It's a very helpful video, and it is very useful if you check that video out, as a lot of these problems, pretty much every one of these problems that I'm going to show you today, will rely on some form of substitution or U substitution. So, now that we know that, let's continue on with our problem. This will get us x over 2 plus 1 by 2 cosine of u du, and then transferring that problem over here, we get x by 2 plus 1 by 2 sine of u, and plugging back 2x in, what we get is sine of 2x divided by 4, actually. Sorry, it needs to be 1 by 2 times this integral also, as we're distributing 1 by 2. It needs to be 1 by 2 over here. So sine 2x over 4 plus x by 2 plus c. Now keep in mind, as for this problem and the last problem, we could apply the exact same method for the other one. So if we did cosine of x squared dx, we could figure out something for that, and that's what we would do. There's an identity for that, but we're not going to do it multiple times, as that would be pretty redundant. Speaking of redundant, it is kind of weird that we're only doing sine and cosine integrals. Let's move on to some other trig functions, mainly secant and tangent. So over here, the integral we will talk about for secant of x and tangent of x advanced strategies is the integral of tangent cubed of 2x times secant squared of 2x dx. So before we do anything, before we go on to all these trig identities, let's first realize that we have a 2x factor in both our tangent cubed and our secant squared. That will be a little more annoying when we have to substitute u eventually and to solve the integrals later down the line. So let's get it done with and substitute u is equal to 2x. So what we will get is 1 by 2 tangent cubed of u secant squared of u du. So now that we have that, what we can do is now a relatively simple process. We can really use some more Pythagorean identities. I know, those identities will be used a lot. And if you're again confused on what Pythagorean identities are, be sure to check out that video in my trig series. All the series are on my channel, and it's going to be under the playlist section of my channel. So be sure to check that out if you don't know what I'm talking about. Now, the Pythagorean identity we're going to be discussing over here is the fact that tangent squared x plus 1 is equal to secant squared x. So this method is incredibly important. This identity is incredibly important, as it's going to derive the rest of what we are going to do. So what we can do is we can first, since we know that there's a secant squared, we could substitute just tangent squared of x plus 1 and then evaluate just tangent and cubed and the tangent to the fifth. Or what we could do is we can isolate the tangent of x. So we can do 1 by 2 tangent of x multiplied by tangent squared u secant squared u. And then, of course, we would have all of that du. So then what we can do is we can rearrange this equation. So we get tangent squared of x is equal to secant squared of x minus 1. So then what we can get is we can get 1 by 2 times the integral of tangent u multiplied by secant squared u minus 1 multiplied by secant squared u du. So now that we have that, we can expand this. So 1 by 2 tangent of u times secant to the 4th u du minus 1 by 2 integral of tangent u secant squared u du. Now you might be like, but that looks more complicated instead of just tangent cubed and secant cubed. You're right, except it does look more complicated, but what we can do is we can do two very simple u substitutions and make this an incredibly easy problem from there. And all that derived by putting secant of x is equal to u for both of these things. So then du is, or let's have actually v, because we're already using u. So dv is equal to secant of u tangent of u. And that's also the reason why this works. With an odd power of tangent, we leave a tangent. And that same tangent can be used with the secant in the u substitution. Now you see, all these techniques play a part. This isn't completely random. Oh, because this random guy on YouTube is saying it. No, these methods lead to simpler problems. There we go. So, what we're going to do is we're going to just take out one power of secant and do our substitutions. So we're going to get 1 by 2 integral of secant cubed, so u cubed du, minus 1 by 2 integral of just u du. Now doing that gives us u to the 4th by 8 minus u squared by 4 plus c. Sorry, v squared. This all needs to be v. All of this needs to be v as we were plugging in v earlier. So now we know what v is, we can plug in u. What v is in terms of u. So secant to the 4th u over 8 minus secant to the squared, or secant square of x over 4 plus c. And plugging in back x for u, that substitution we made all the way at the very beginning, we get secant to the power of 4 of 2x over 8 minus secant squared of 2x over 4 plus c. And there you have it. This is the solution to this problem. Now, if you thought this was long, imagine how long it would take if you had done it the other way for substitution. If you had done tangent, then you would have to have just regular tangent cubed of u, then you would have to do another secant squared identity and solve two separate integrals from that. So you would be solving like 3-4 integrals, versus this, you got two integrals with a very easy u substitution. So there you have it, a very fun and very interesting integral involving secant and tangent of x. But there is one final thing. We've covered a lot of the trig functions, but my video before this was trig substitution, which you should definitely check out as you're going to need it for this problem. But in that video, I was talking about how trig substitution is used in these advanced trig integrals. So today, we will bring that to fruition with all these different identities and methods to algebraically solve these integrals. With trig substitution, we will be solving one final integral. So enjoy, and let me show you how to solve an integral with trig identities and trig substitution. And there you have it. your great and final integral awaiting you on this journey to master trig integrals. But what is this? That doesn't look very climactic. That just looks like some random, function, that could probably be integrated with, u substitution or something. But no. This integral will actually use trig substitution and the trig identities techniques that we have covered in this video. So, for that, let us begin on solving this problem. So, for those of you who don't know what trig substitution is, you're going to need it for this problem. So, make sure that you watch my trig substitution video, which was the one right before this one. So, for those of you who do know, let's do a quick rundown. Let's draw our triangle, or if you remember that we are going to substitute tangent of x. So, what basically is we have x1 and the square root of 1 plus x squared. Now that is theta over there. Now, as you can see, what we have over here is we have x is equal to tan theta. Now, c1 plus x squared root is equal to secant of theta. And that's because hypotenuse over length, this side over this side, is equal to secant of theta. Now, besides that, we don't know what this thing is. Well, if you square both sides of this equation, we get secant squared theta is 1 plus x squared, but we have to square it again. So secant to the fourth theta is equal to 1 plus x squared squared. We know that, but what about dx? Well, just differentiating gets us secant squared theta d theta. So we can plug all that in and we can go to solving this problem. So this integral becomes 1 over secant to the fourth theta multiplied by secant squared theta d theta. And what we can do is we can just simplify. So we get 1 by secant squared theta d theta. But notice how this is also equal to the integral of cosine squared d theta. But hey, did we just solve this integral like a couple minutes ago in our second problem? Absolutely, you're right, we did. So we can plug in back those results to figure out what this is in terms of theta. So what we get is sine of 2x by 4 plus x by 2. That is our integral. And we add c to this. But we have to substitute theta over here and theta over here. But what is theta then? Well, let's look at this equation over here. X is equal to tan theta. Solving for theta, we get theta is equal to tan inverse of x. So let's plug that in. Our final answer then becomes sine of 2 times the tangent inverse of x over 4 plus the tangent inverse of x over 2 plus c. And that concludes our final problem and its explanation. You now have seen a bunch of trig integrals and even one that used all the techniques we've learned in the past couple of videos. These are incredibly useful techniques and will really help you all throughout your math career. But biggest thing is you learned something, and that's always a good thing, and everyone should strive to learn one new thing every single day. So, I really do hope you enjoyed this video. You watching this video, the viewers, are the best part of what I do. And if you enjoyed this video and found it educational and helpful, please make sure to like, subscribe, and hit that notification button, as it really helps out the channel a ton. And be sure to comment down below anything you have for this channel, as long as it's kind and respectful. So, thank you so much for watching this channel. See you in the next one, and bye-bye.